Okay, so my drawing that is really just to reinforce that when we're changing the coefficients, we're just adding more of the same molecule, because we know when chemical reactions occur, it's never just one molecule. Remember, our moles are these huge numbers, so we always have huge, astronomically large numbers that we're working with. Okay, so we've got plenty of atoms that we can react. Okay, so that's all very well and good, but how do we do this? So first, all right. I have this equation over here. This is a combustion reaction. This is going to be our example that we're going to work. So whenever we take a hydrocarbon, that is something that has carbon and hydrogen like this does, and we burn it, combustion means burn, so usually there's going to be oxygen, we end up with the same two chemicals, carbon dioxide and water. So this is methane, CH4 is methane. I could do this with propane. You've probably heard of propane for like grilling gas, or sometimes people heat their homes with it. Butane is in those lighters, the long clicker lighters, those have butane in them. You're always getting carbon dioxide and water. Okay, so we're going to balance this. That's going to be our example for how we do this method. So yes and check is always a valid thing to do, which is kind of what we did in looking at this. We didn't have a particular order we were going in. We were just kind of like, okay, that looks like a good number to change. This looks like a good number. If I have lots of pure elements like hydrogen and oxygen, those are pure, that's fine to do. But if everything you have is molecules with lots of other atoms in it, it's a good idea to have a way to go about doing this. So first we're going to prioritize, and we're going to look at where the different elements are in the equation. If I have a pure element like oxygen here, when I change that coefficient, I'm not changing any other element. So that's a good thing to do last, because I want to finish with something that's not going to make me go back and change other things. Okay, so we're going to save pure elements for last. The other thing that we're going to look at is if an element appears more than once on a side. So of course they're going to appear on both sides, but if I look at this equation, I've got oxygen in both of my products. And that's going to make it harder to balance, because if I change the oxygen on one side, I have to think about it appearing in two places on the other. So usually what we do is we balance everything else first and then hope that that oxygen sort of works itself out. So instead of saying last, I'm going to say later, because if I have to make a choice, I want to save the pure element for last. But I do want to kind of wait on anything that involves multiple ones. Okay, so what are we going to do? I usually just start at the front and go forward. But if you see something right off the bat that like, oh, clearly I need to change that, go for that. So you're going to pick an element that doesn't fit this first rule, and you're going to balance it. And once you've balanced it, then you're just going to keep that process going for the other ones. So if I look at my carbon, since that's my first element, I see that there's one carbon on each side. So I don't really have to do anything. So over here, I only had two. What do I have to do here? How am I going to get four hydrogens? put a 2. Okay, so coefficient times subscript is 4 hydrogens. A handy way to count your atoms, I guess I'll put this here. Count the atoms by multiplying the coefficient and the subscript. So COEF is coefficient. Okay, so now I've come to oxygen. So I've got the pure element on one side. So I'm going to look at the other side first. And then I'm going to come back to the oxygen here to do the final balance. Or if you like, draw out the molecules and count them. Okay, so now I'm at the oxygen. And I've got 2 from here plus 2 times 1 gives me 4. So when I go over here, I'm going to say, here's 2. What do I need to put up here? A 2. Because 2 times 2 is 4. All right, now the last step is going to be to kind of do this, go back and double check to make sure all your atoms add up. But there's one more step that comes before that that doesn't apply to this equation. Okay, so I'm going to erase this, do another one so we can do step 3, and then we'll write down step 4. All right, anybody still need this information? Okay, good. So we're going to do a combustion reaction again, but instead of methane, meth means 1 carbon, we're going to do ethane. Eth means 2 carbons. So it looks very similar. We still have oxygen, same products. And I'm going to unplug this for a second. A little bit easy. Okay, so this time I got to do something with the carbons because I've got 2 carbons on this side. So I'm going to put a 2 over here. And remember that if I don't have a coefficient or a subscript, that's that invisible 1. So invisible 1 times 2, invisible 2 times 1. Okay, I go into my hydrogens. Over here I've got 6. Over here I only have 2. So what am I going to do? I got to put a 3. Okay, now remember, this is multiplying. This isn't adding. I'm not adding 3 water molecules. I am multiplying that water molecule by 3. So 1 times 3 is going to give me 3 water molecules. Okay. So this is 3 times 2 equals 6. And then my oxygen is 3 times. 3 times 1 is 3 oxygens. Okay, but I have oxygen in 2 places, so make sure you're counting all the places. So over here, I have 2 times 2 is 4, so I have a total of 7 oxygens. All right, everybody see why we have 7 instead of just one of those other numbers? All right, so this is where we come into rule number 3. When I come back over here, can I put a whole number here to give me 7 atoms? Okay. The reason is, whenever I have a subscript that has an even number, then no matter what I do for the coefficient, I'm always going to end up with an even number. I'm always going to have an even number of oxygens on this side, so I have to make that be an even number. So, rule number 3. What I call an even-odd conflict. I've got an odd number on one side, but I'm forced to have an even number on the other. You're going to multiply the coefficients that you've already addressed, you've already looked at them, by 2. You're going to double. All right, so clearly I need to multiply these by 2. That's going to become 4. That's going to become 6. Even though I didn't change this one, I was using this one to figure out what those coefficients were. So this is going to become a 2 as well. So now I'm going to have to go back and look at how many I have of everything again. I now have 2 times 2. It's 4 carbons. 2 times 6. 12 hydrogens. This is just a 4. This is 6 times 2 is 12 hydrogens. So I'm still balanced on those. As long as I do it for everything I've already looked at, then it should stay the same. I haven't done anything with this oxygen yet, which is why I didn't mess with it. Okay. So my oxygens on this side now are 4 times 2, coefficient times the subscript, plus 6 times 1. What does that give you? 14, which is double the 7 that we had before. So it makes sense. If we doubled everything, we should end up with double that. We have 14 oxygens. So now if I want to have 14 oxygens on this side, what do I have to do? Multiply by 7. Okay. And then of course your last one is check by counting atoms on each side. We will do more balancing on Monday, but we need to talk about different types of equations for ionic compounds. So far we've had pure substances in everything. There's been a pure element, either oxygen or hydrogen in each of the equations, but sometimes everything's a compound. If they're all ionic, we can represent what's going on in a couple of different ways. So I'm going to start with this. We're going to balance it. Now, normally when we are writing the equation for balancing purposes, we leave out the phases. But in this chapter, those phases are going to be important because they're going to tell us what's going on with these ionic things. Okay, so a couple of things to pay attention to here. First of all, we don't have any pure elements, so we can't save them for last. But we also have more elements because we have the nitrogen and the oxygen in here together. Now, you can separate them out, and that's how I'm going to do it. But when you have a polyatomic ion appear the same on both sides, especially if that's the only place those elements are, so nitrogen and oxygen are in nitrate here, nitrogen and oxygen are in nitrate here, I can just think of those as one thing. And I could just balance nitrates rather than separating them out. If you want to do it that way, that's fine. I'm going to do it by elements because that's what we've been doing with everything else. So our potassium and our potassium already balanced. Our chlorine and our chlorine not already balanced. So what am I going to do? I'll put a 2 here. And my lead and lead already balanced. And now I have this N. So this is a little bit harder. So I'm going to put the N and the O. 2 times 1. So I multiply with the parentheses. I multiply the outside of the parentheses by the inside of the parentheses by the coefficient. So 3 numbers. So 2 times 1 is 2. And my oxygen is 2 times 3 times 1. Outside, inside coefficient. And that's 6. On this side, I have 1 nitrogen and I have 3 oxygens. Oops. So how can I fix that? Yeah, I'm going to put a 2 in front of potassium nitrate. And so multiplying those, I get 2 and 6. Okay. Then that was my last one. So I would go back through and check. Potassium's balanced, chlorine's balanced, lead is balanced, nitrogen is balanced, oxygen is balanced. Okay, so they don't tend to be too bad. A lot of times you end up with like 1, 2, 2, 1 or 1, 1, 1, 2. So these don't tend to be too bad. Problem with this is this isn't really a good representation of what's going on in the beaker. Now, I hate this term that I'm going to give you, but it's what chemists use. We would call this the molecular equation. I'm going to put that in quotes because these are not molecules, okay? Molecules stay together in water. These do not. All right, as soon as these ionic compounds hit the water, they split up and they go their separate ways. All right, you take your family to the fair, everybody goes in different directions. Same thing with these ionic compounds, everybody goes in different directions. So it would be more appropriate to write this. So I took KCl and I broke it up into a +1, -1, and I put a 2 in front of each of it because I've got a coefficient of 2. I can tell this is lead 2+ because I've got 2 nitrates. But when I get to the solid, it stays together. Okay, that's not dissolved, so it's just going to sink down to the bottom. All right, this is kind of a pain in the butt to write. It's kind of a pain in the butt to look at. There's too much going on there. We call this total ionic. So we like to simplify this. If I were in algebra and I had an X on each side of the equation, I'd cross it out. 2 potassiums, 2 potassiums, 2 nitrates. Oops, this is supposed to be 2. 2 nitrates. They appear the same on each side. I can cross them out. We call these spectators. And everything that's left over becomes what's called the net ionic equation. Okay, so these are the 3 terms you need to know: molecular, total ionic, and net ionic. And actually, you should know spectator ion too. So the spectators are the same on both sides, so they're not involved. They're like the people in the bleachers. They don't get to play in the game. They're just watching what's going on. So we leave them out and focus on what's on the field.